Here's some pressure estimating related to vomit. When you vomit, your stomach forces fluid to flow out through your mouth. So we're going to treat the stomach, esophagus, and mouth as a 1 centimeter radius tube that's 60 centimeters tall, and it's vertical, of course. So we're assuming just standing up vomiting like this, not the classic, bent over. So what gauge pressure would your stomach have to apply to get the vomit to come out at 1.5 meters per second? All right, well, clearly this is let's see, how am I going to draw this? Stomach, esophagus, mouth here, right, and then you around it. Let's see, that's not working out too well, is it? All right. That's actually not bad. No arms. Okay, so here you are and you have the fluid, and you want the fluid to come out at 1.5 meters per second. So how hard, how much pressure, how hard do we have to squeeze? So we have flowing fluid. So this is Bernoulli's equation problem. And in Bernoulli's equation, you always pick two places and you take that expression and it has to be equal in each place. So we're going to take sort of like the stomach at 1, and as the fluid comes out at 2. All right. So let's see. Let's do stomach, and the expression has to be same as it exits the mouth exit. Because remember, there's that important point that it's the gauge pressure. The pressure out here will just be atmospheric pressure. Anyway, here we go. So in the stomach, you've got atmospheric pressure plus whatever we're applying. So this is really what we're looking for. How much gauge pressure do we have to apply in the stomach at 1? Plus the density of the fluid, GH, and now we're pushing fluid up. So the potential energy term is going to matter, the rho GH term. So we better think a little bit carefully here. So it's 60 centimeter vertical tube. So this bend isn't really there. We're just treating it as a vertical tube. So what that means is we would want to think of our y-axis kind of like that, and probably put the stomach at 0 and put the mouth at 0.6 meters. So that means the h we put here really is going to be 0. The 0 potential energy, because this is the low part. Plus 1/2 rho v1 squared. H1, right? All right, so that has to be equal to whatever's happening at the mouth. So the mouth is right after we come out of the mouth, so it's an atmospheric pressure. And that's the total pressure. There's nothing applying extra gauge pressure there. The height here will be rho GH2. So up by 60 centimeters, and then it'll have some speed here, 1/2 rho v2 squared. So let's look at this and think, what do we need, what do we got, what do we have to solve for? The atmosphere will cancel. So we don't care about the atmospheric pressure. I meant to say, so your body is soft, so the atmospheric pressure does get transmitted, we're saying, into your stomach. And also the hint was what gauge pressure is needed in your stomach. So when I say that, that implies there's also atmosphere that we're going to subtract off. Okay. Anyway, back to where we were. We're looking for that. These two terms, I'm going to say that one is 0, because we're going to say H1 is 0. By setting the origin at the stomach, there's nothing here. This is the term that will have the 0.6 meters in it. Let's see. So that'll be the 0.6 meters. Here we know it comes out at 1.5 meters per second. So we do know that. And we know the densities. That's all good. What about here? So what are we going to use for the velocity in the stomach? Well, we're actually going to use continuity. Typically that's what you use when you need, you're missing a velocity. But what does continuity tell us this time? In this problem, it said treat it as a single tube with a single radius. So if we're really pretending that this tube, the stomach, is a tube that has the same radius all the way through the esophagus and out the mouth, then the cross-sectional areas are the same. So really, we have, to work it out, you'd say A1 V1 equals A2 V2, but A1 equals A2. So therefore V1 equals V2. So for this problem, these are the same V's right there. So what does that mean? That actually means they cancel, right? The same term. So the fact that the fluid is going at the same speed is what tells you that that term isn't going to contribute any differently to the pressure on each side. So you just leave them out. So in the end, all we really have is that the pressure we're looking for is really what is just the hydrostatic pressure to get the fluid out. All right, so then the P1 we're looking for is the density, which is 1,000 because it's vomit and water have the same density. Depends on what you ate. 9.8 and 0.6. And there it is. And if you work that out and you want pressure, you'd get 58. Oh, I can't read my handwriting. 5880, I think. Oh, pascals. Newton per meter squared. And you can reality check. Is that like 10 atmospheres or something? No, this is a small number compared to atmospheric pressure, a typical gauge pressure, a nice low pressure. And, you know, the problem's a little unrealistic that we have this constant diameter and the same velocity. We could have put more in the problem, made the stomach's diameter bigger, and then continuity would have made it more interesting. These wouldn't have canceled, there would have been more terms. But for some reason, we just wanted to simplify this one and just illustrate how to deal with the heights.